Imagine like drug discovery,
Sure.
not being this uh, slow and difficult thing, but where AI helps us predict how proteins interact, leading to life-saving drugs so much faster. And that's like the promise of graph convolutional networks.
Just yeah.
Yeah, exactly. And that's why we're diving deep into a fascinating research paper called SuperGCN, General and Scalable Framework for GCN Training on CPU-Powered Supercomputers.
Yeah, this paper really caught my eye because it tackles a major roadblock in the world of GCNs, which is training them on massive data sets. Like we're talking about data sets that are so large they can bring even supercomputers to their knees.
Okay, so before we get too far ahead of ourselves, I think we should take a step back. And for those of us who aren't uh, AI experts, can you explain what a GCN is
Yeah.
and why these massive data sets are so important?
Absolutely. So think of a social network like Facebook. You have individuals or nodes and the connections between them, or edges representing their friendships. A GCN can analyze this network to understand how information, like trends or opinions, might spread.
I see. So it's about understanding relationships, not just isolated data points.
Exactly. And these relationships can be found everywhere. In biology, we can create a graph representing proteins and their interactions.
Oh, wow.
A GCN can then help us predict unknown interactions, potentially leading to breakthroughs in, drug discovery.
So the larger the data set, the more complex and nuanced these relationships become.
Yeah.
And then the more powerful our predictions can be, I guess that makes sense. But you mentioned a roadblock.
Right. So when these graphs become huge with millions or even billions of nodes, training GCNs becomes incredibly resource intensive. You need immense amounts of memory, and the communication overhead between different parts of the graph can be a real nightmare.
So how do researchers typically deal with this?
So there are two main approaches, full batch training and mini batch training.
Okay.
In full batch training, you process the entire graph at once, which is ideal for accuracy but incredibly demanding on memory. Mini batch training, on the other hand, processes the graph in smaller chunks.
Okay.
Easier on resources, but risks losing crucial information about the overall structure.
So it's a trade-off
Yeah,
between accuracy and efficiency.
precisely. And that's where Super GCN comes in. This framework proposes a way to do efficient full batch training on giant graphs. But here's the catch. They're doing it on CPUs, not the powerful GPUs that typically dominate the world of AI.
Really, CPUs? That's
Yeah.
surprising.
Yeah.
I thought CPUs were way slower than GPUs for these types of tasks.
That's what I thought too. But the researchers behind SuperGCN have made some really clever optimizations,
Okay.
both at the single CPU level and across multiple CPUs, allowing them to achieve some truly impressive results.
Okay. Color me intrigued.
Yeah.
Let's start with the single CPU optimizations. What did they do to make these typically slower CPUs perform so well?
They identified that the aggregation process, where each node gathers information from its neighbors, was a major bottleneck.
Okay.
Imagine each node having to call up all its friends to get the latest gossip. It gets chaotic fast.
Ah, I see. So they needed to streamline that process somehow.
Exactly.
Yeah.
And they did this through a few key improvements. First, they optimized memory access patterns by clustering and sorting data, ensuring that the CPU can access the information it needs quickly and efficiently.
So it's like organizing your workspace.
Yeah,
So you don't waste time searching for things.
a perfect analogy.
Mhm.
Second, they introduced multi-threaded parallelism and load balancing, cleverly dividing the work between the CPU's cores to avoid any single core becoming overwhelmed.
So like having a team of workers
Yeah,
efficiently tackling different parts of a larger project.
exactly. And finally, they developed register-optimized kernels. These are specialized instructions that take advantage of how data is stored within the CPU itself, squeezing every ounce of performance out of the hardware.
So they've basically turned these humble CPUs into lean, mean GCN training machines.
Precisely. But that's just half the story. When you scale up to multiple CPUs, things get even more interesting. Now you have the challenge of coordinating the aggregation process across all these CPUs, which involves massive amounts of data being transferred between them.
Okay, so how did they tackle that communication bottleneck?
Well, this is where they got really innovative. They introduced a method called hybrid pre and post aggregation.
Oh.
Imagine it this way. Instead of every node having to call up all its friends individually, they strategically prearrange some group calls
Uh-huh.
and then only follow up with individual calls when absolutely necessary.
Ah, that's clever.
Yeah.
So they're minimizing the overall amount of communication between CPUs?
Exactly. And to visualize how this works, they provided a helpful diagram in figure 4D of the paper. It clearly shows how this approach reduces the amount of data that needs to be transferred, making the whole process much more efficient.
Okay, I'm starting to see how they're achieving these impressive speedups, but there's got to be more to it, right? Especially when they're dealing with such massive amounts of data.
You're right. There's one more trick up their sleeve, and it's a bit of a head scratcher at first. It's called into quantization.
Into quantization. That sounds intense. What does it involve?
Essentially, they compress the data being transferred between CPUs by representing it with only 2 bits.
Wait, only 2 bits. That sounds incredibly risky. How can they possibly maintain accuracy with such extreme compression?
That's the million-dollar question, and it's where things get really fascinating. So, to counteract the potential for accuracy loss, they introduce another clever technique, label propagation.
Okay, I'm all ears. Tell me more about this label propagation magic.
Imagine you're trying to decipher a coded message where most of the letters are missing.
Yeah.
It'd be nearly impossible,
Right.
right? But what if you had a few key letters sprinkled throughout the message? Suddenly, you'd have a much better chance of figuring out the missing pieces.
Ah, I see where you're going with this.
Mm.
So the label propagation acts like those key letters,
Exactly.
providing enough context for the network to make sense of the compressed data.
Exactly. So they strategically embed labels into the features of a small set of nodes.
Okay.
These labeled nodes act as anchors, guiding the network and allowing it to learn relationships even with the reduced precision of the transferred data. It's a remarkably effective technique.
This is all blowing my mind. So they're
Yeah.
optimizing memory access, parallelizing tasks, squeezing performance out of the CPU's architecture, cleverly managing communication between CPUs, and then compressing the data itself with this into quantization and label propagation magic. It's like they've orchestrated a symphony of optimization techniques.
It truly is. But the big question remains, does it actually work? Can they really achieve comparable results on CPUs, and at what cost to accuracy? Let's dig into the performance evaluations and see what they found.
Okay, let's see if SuperGCN lives up to the hype.
So to really put SuperGCN through its paces, they ran it on 2 different supercomputers.
Okay.
First up was ABCI, a system powered by Intel Xeon CPUs,
Okay.
where they tackled 2 very different graphs.
Uh-huh.
Ogbian products, representing relationships between products, has a more structured, predictable layout.
Okay.
Then there's Reddit, the social network we all know and love, with its sprawling, chaotic structure.
Two very different beasts indeed.
Oh,
I'm guessing that presented some unique challenges for SuperGCN.
absolutely. But that's what makes the results so compelling.
So,
On both datasets, SuperGCN showed significant speedups compared to the existing best CPU solution, especially as they scaled up the number of cores.
yeah.
On Reddit, they achieved up to a 4x speed increase, meaning a task that might have taken a week could now be completed in under 2 days.
Wow, that's a significant time saving. So it's not just about raw processing power, it's about how efficiently SuperGCN utilizes those CPU cores.
Exactly. And when they broke down the runtime, it became clear that the single CPU optimizations were crucial for Ogbian products,
Yeah.
while the communication optimizations really shone on Reddit.
Okay.
It's like they had the right tool for each job.
It makes sense. Optimize for the specific challenges of each graph. But what about those truly massive graphs, the ones that make even supercomputers sweat?
Yeah.
Did they dare to test SuperGCN on those?
Oh, they absolutely did. For that, they moved over to Fugaku, a supercomputer powered by ARM-based Fujitsu A64FX CPUs.
Okay.
They chose 2 behemoths for this test.
Ah.
OGB Papers 100M, a citation network of scientific papers,
Okay.
and OGB LSC Mag 240M, an even larger academic graph.
Wow.
These are the kinds of data sets that can make even seasoned researchers break out in a cold sweat.
And this is where they push the scalability to the limit, right up to thousands of CPU cores.
You bet. And the results were nothing short of remarkable. SuperGCN scaled beautifully on both datasets,
Okay.
demonstrating its ability to handle graphs with billions of edges.
That's impressive, but they keep coming back to the accuracy question.
Yeah.
Did they maintain good performance on those massive data sets, even with the into quantization.
Right.
I mean, squeezing all that information down to just 2 bits sounds almost too good to be true.
You're right to be skeptical on these truly massive graphs. Simply using into quantization did lead to a noticeable drop in accuracy compared to the standard FP32 precision.
Yeah.
But here's the kicker. When they combined into quantization with label propagation, the accuracy bounced right back up, matching the FP32 results almost perfectly.
So label propagation really is the key to maintaining accuracy when you're pushing the limits of data compression.
Hmm.
It's like having a few landmarks in a vast uncharted territory.
That's a great analogy. Those strategically embedded labels provide just enough context for the network to navigate the compressed data landscape and make accurate predictions.
Okay, so they've proven that SuperGCN can handle massive data sets on CPUs with impressive speed and accuracy. But how does it stack up against the reigning champions of GCN training the GPUs?
Yeah.
Did they dare to make that comparison?
They did, and they chose Ogbian Papers 100M as the battleground.
Okay.
They pitted SuperGCN running on a cluster of A64FX CPUs against BNS GCN, a state-of-the-art GPU-based solution running on powerful NVIDIA V100 GPUs.
Okay.
They ensured a fair fight by using a comparable number of processing units on each side.
So a true clash of the titans. What happened?
Even without any of the fancy communication optimizations, SuperGCN was already 2.5x faster than BNS GCN.
Yeah.
That's impressive in itself, considering the reputation of GPUs in this domain.
That is impressive. But BNS GCN is known to sometimes sacrifice the full graph structure for speed. Did SuperGCN manage to preserve that while still being faster?
That's the best part. They ran the test again this time, enabling all of SuperGCN's communication optimizations, including the hybrid pre- and post-aggregation, and of course the into quantization with label propagation. And get this, they achieved a speedup of 6.7x over BNS GCN while maintaining the full graph structure.
Hold on. Did you just say 6.7 times faster than a state-of-the-art GPU solution on CPUs? That's groundbreaking.
It really is, and there's another bonus. A64FX CTUs are known for their energy efficiency, meaning SuperGCN not only runs faster, but also consumes less power than the GPU-based solution.
Wow.
It's a win-win on both the performance and sustainability fronts.
This is truly remarkable. It challenges the conventional wisdom that GPUs are the only way to go for serious GCN training. But as with any breakthrough, I imagine there's still some limitations.
Of course, SuperGCN isn't a silver bullet. It still faces challenges when dealing with extremely complex graph structures or tasks requiring real-time inference speeds, and there's always room for improvement in terms of fine-tuning the optimizations for specific hardware and datasets.
That's understandable. But even with those limitations, this feels like a paradigm shift in GCN training. It opens up so many possibilities for analyzing and understanding large-scale datasets that were previously considered out of reach for CPUs.
I completely agree, and the implications go far beyond just technical achievements. The fact that they've achieved this level of performance on CPUs, which are more widely available and often more cost-effective than GPUs, is a game changer.
It democratizes access to these powerful AI tools,
Yeah.
making them available to a wider range of researchers and industries. Imagine small research labs or startups being able to tackle complex problems that were previously only accessible to large corporations with deep pockets.
Exactly. It levels the playing field and opens up a world of possibilities for innovation, and that's what makes this research so exciting. It's not just about pushing the boundaries of what's technically possible, it's about making these powerful tools accessible to everyone.
I'm really curious to see what kinds of real-world applications emerge from this. Can you give us a glimpse into the potential of SuperGCN?
So the potential applications are incredibly vast
Yeah.
and span across numerous fields.
Okay.
Let's start with something we're all familiar with, social media. Imagine using SuperGCN to analyze real-time social media trends, understanding how information spreads, identifying influencers, and even predicting the next viral sensation.
That would be fascinating.
Yeah,
Marketers would love that kind of insight.
absolutely. But the applications go far beyond marketing and healthcare. We could use SuperGCN to personalize medical treatments.
Okay.
Imagine analyzing a patient's unique genetic makeup, their medical history, and even their lifestyle choices to create a graph representing their individual health profile.
Yeah.
SuperGCN could then be used to predict their risk for certain diseases, identify the most effective treatments, and even recommend preventative measures tailored to their specific needs.
That sounds like the future of personalized medicine.
Yeah.
moving from a one-size-fits-all approach
Yeah.
to something truly tailored to the individual.
Exactly. And think about the possibilities in finance.
Okay.
Super GCN could be used to model the entire financial system,
Wow.
analyzing the complex relationships between banks, businesses, and individuals.
Yeah.
This could help us predict and mitigate systemic risks, prevent financial crises, and even identify opportunities for investment.
So it's not just about understanding data. It's about understanding the connections and relationships that drive complex systems.
Precisely. And this ability to analyze relationships at scale has the potential to revolutionize fields like uh, urban planning, transportation, climate modeling, and even cybersecurity.
It sounds like Super GCN is giving us a new lens
Yeah,
through which to view the world, one that allows us to see the interconnectedness of everything.
that's a beautiful way to put it. But as with any powerful technology, there are ethical considerations to keep in mind.
Right.
As GCNs become more powerful and accessible,
Yep.
we need to ensure they are used responsibly and for the benefit of society as a whole.
Mhm.
We need to be mindful of potential biases in the data, the implications for privacy, and the possibility of misuse.
That's an important point. It's crucial that we develop these technologies with a thoughtful and ethical approach,
Yeah.
ensuring they're used to solve problems and improve lives, not create new ones.
I couldn't agree more. The future of GCNs is incredibly bright, but it's up to us to steer it in the right direction.
Well said. So, as we wrap up this deep dive into Super GCN, what are the key takeaways you hope our listeners will walk away with?
First and foremost, I hope they see that the landscape of AI is constantly evolving,
Yeah.
and even seemingly humble CPUs can achieve remarkable things with the right approach. Super GCN demonstrates that innovation can come from unexpected places, challenging our assumptions and opening up new possibilities.
I think that's a valuable lesson.
Yeah,
Never underestimate the power of creativity and ingenuity, even when working with seemingly limited resources.
absolutely. Secondly, I hope listeners grasp the sheer breadth of potential applications for JCNs,
Yeah.
from social media to healthcare finance to climate modeling. This technology has the power to transform the way we understand and interact with the world around us.
It's truly mind-boggling when you start to think about
Yeah.
all the possibilities.
And finally, I hope this deep dive has sparked a sense of curiosity and excitement about the future of AI.
Yeah.
We are just scratching the surface of what's possible, and it's an incredibly exciting time to be following this field.
I completely agree. And to our listeners, we encourage you to keep exploring, keep asking questions, and keep pushing the boundaries of what's possible. Who knows? Maybe you'll be the one to discover the next breakthrough in GCNs or another AI field.
Until next time, keep diving deep.